Okay, looks like this is chemistry video, Chem25BBlake. We're in week 2-5. And we're just doing Lewis structures. And keep these directions handy in here. This is page 2 of the flip charts. I'm just going to be using these directions for several more examples. This would have been iodomethane, CH3I. We did NF3, which would be nitrogen trifluoride. We did NH4+, which would be the hydronium ion. You should know the name of that one. So we got 3 done, and we'll probably try 3 more. Now we have the nitrate ion. Now, not sure why I did this one next because it's a little bit complicated, but that's okay. This one's got 2 things going on. One, when we get up to this part for nitrate ion, when we add to determine the total number of electrons, and we check to see if we have a charge, yeah, we do. It's going to be NO3 minus, you should know that, 1 minus. It's going to have an extra electron, so we have to add 1 in. But when we get down to this part, we add up the electrons to determine the bonds, it's not going to be right. So then what do we do? Okay, we have a double bond to fix it and a triple bond, or in some cases you have a triple bond, but in the case of nitrate, you got a double bond to fix it. So those things that are going to happen are going to be different than these 6, 7 steps there. Let's just walk it through the way we know how to do it. We've got to list the now. This is going to be like, how am I going to remember to do all this? Once we do some more of these, you'll be okay. You've got to list all the atoms, put the electron dots on there, add to determine the total number of electrons. Okay, so we have NO3 minus. All right, so we have a nitrogen atom, and an oxygen atom, and an oxygen atom, and an oxygen atom. And we have to add them up. When we get that total, it's going to be off by 1 because of that charge. Nitrogen is here, has 5 valence electrons. Oxygen is right beside it, has 6. So you have to put those in. Nitrogen has 1, 2, 3, 4, 5. Oxygen has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Add them up. 6, 12, 18, 19, 20, 21, 22, 23 electrons. The problem is this is minus, which means it has an electron extra. So we have to add an electron that is negative, so we end up with 24 negative electron charges. Now we need a central atom. Which one do we pick? Well, not only is nitrogen the odd one out, but it's closer to carbon. So put nitrogen in the center, put an oxygen here, here, here. By the way, I could have my 3 oxygens here, here, and here. Or here, here, and here. Or here, here, and here. That won't matter. You're going to end up with the same answer every time, regardless. Next, according to the list, you have to write a skeletal structure, which you just did, add in the shared pairs, then place octets, then count. Here's our shared pair. Then we want to give everybody 8. Now there are exceptions to that. I think we've already run into hydrogen as an exception. There are other exceptions we're going to run into soon enough. We could try to put those off a little bit. Okay, but oxygen and nitrogen both get 8. So nitrogen gets 2 more, so it has 8. Oxygen gets 2, 4, 6 more, so it has 8. 2, 4, 6 more, 2, 4, 6. Now everybody has 8, 8, 8, 8. And now we add, and here's where we run into a problem, because we should get 26. There's 8, 16, 24, and those two makes 26. So we have a problem. And the way you do this, when you have too many, is you delete 2 from the central atom. Now, you don't have to do it from the central atom, however, it is way easier to do it from the central atom. And then you move 2. So anytime you have a multiple bond, this is what you do. So what I'm going to delete is the ones off the central atom, which is the nitrogen. And I'll just, it can be that one or this one or this one, it doesn't matter. Actually, never mind, the one I want to delete is these guys, sorry. I can move them in here from here or there for there. This is harder to see because you have to think 3-dimensionally. So I'm going to move this pair up here. Once I do that, I'll have this. And then this oxygen will have 2 sets in there. That set and this set, that's a double bond. And we're going to be talking about something coming up called valence shell electron pair repulsion theory, which is going to happen here. But for our purposes, we'll just replace with sticks. So I have a double bond oxygen with its electrons, nitrogen. I got this a little close. We'll move it. Now the story isn't over after I get done drawing this because other things are going to happen, but this is nonetheless the Lewis structure. Shared pair there is a stick with an oxygen, dot, 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 dot. Shared pair there, so we got a stick with an oxygen, dot, 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 dot. And what I have, there's more motion that occurs after this, but I'll tell you what happens, is you got all this space down here with no electrons in it, all 180 degrees, and these are kind of bunched up, they push away from each other. And these electrons will push down into this space and go out on the sides. That's what valence shell electron pair repulsion is. We're going to talk more about it later. But that one would result in this molecule, I think. And then this is supposed to show what's going on with resonance. So it behaves as if it's some this, some this, some this. Sometimes people like to say it's as if it's changing back and forth very quickly between them. But it's really more like it, you know, this bond is partly double, this bond is partly double, this bond is partly double, and it acts like a hybrid of all these. I shouldn't use the word hybrid. It acts like it's somewhat all of these at the same time. Okay, let's go to another example. Next example is this ion. What was this? 42. You should know this ion. ClO4 minus. What's that guy? What's its name? Well, I got chlorine over there with one. Well, let's just get them all listed first. We'll move this over because I'm going to need a little more room this time. Chlorine, oxygen, 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 oxygen. Chlorine, 1, 2, 3, 4, 5, 6, 7. Oxygen, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oxygen's in the 6th column, has 6 valence electrons. 6. Chlorine is there, has 7. And there's 4 oxygen and a chlorine. The minus charge. That is the perchlorate ion. So if we go back to the directions, we listed the atoms, place the electrons, dots, we're going to add them up. This time we have a charge, and so I've got to add in an extra electron. We'll put octets in. The bonds will add, or the electrons should add up this time, so I won't have multiple bonds on this one. Okay, so we add them up. We have 6, 12, 18, 24, 25, 26, 27, 28, 29, 30, 31. We have 31 electrons, but that is negative, so we have to add in another extra electron, total of 32. Now we need a central atom. Well, chlorine is the odd one out, and okay, this is going to break my rules. Oxygen is closer to fluorine. And I said earlier, if you go back, well, halogens aren't usually your central atom, or something to that effect. Well, that's correct, but they can be. It's weird, and it doesn't really work out that often, but halogens can be your central atom with oxygen around. So let's put chlorine, even though this is breaking our rules, around in the middle, surrounded by oxygen. The next thing is to give everybody 2 electrons shared. There's 2, there's 2, there's 2, there's 2. The next step is to give everybody a full octet, except for hydrogen and some other exceptions coming up that we're going to look at. Okay, so there's 8, 2, 4, 6, there's 8, 2, 4, 6, there's 8, 2, 4, 6, there's 8. Then we add, when we add all those up, that's 32. So we put sticks in for shared pairs and we're done. I forgot something on the last page. Don't forget your unshared pairs. 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. And you're not done until you put a bracket around it and give it the extra charge. That extra electron is somewhere in there and you can't tell where. What I didn't put on the last one was the bracket. I got in a hurry to go show you this page and I forgot to do it. Okay, so I got the bracket, and one of these, somewhere in there, is the extra negative charge and you can't tell where it went. Let's see if I have time for one more. It's pushing it. Let's see what it is. But we can also go quicker as long as it doesn't have anything new in it. CS2. Okay, it's not too bad. CS2. It means you have a carbon, which has 4 dots, and a sulfur. Sulfur is just below oxygen, so they have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. What do? Add them up. 6 and 4 is 10 plus 6 is 16 electrons. There's no charges on this. It is not a polyatomic ion. It is carbon disulfide. It's kind of a lot like carbon dioxide because sulfur's in the same family as oxygen. So we could put carbon in the center and put a sulfur on either side. You can put it top and below. You can even put them at 90 degrees. Weird, but it can work. Put the shared pair in. Give everybody 8. 6 more gives that one 8. 6 more gives this one 8. And 2 here and 2 here. Now what's the next step? Add. We don't have charges to worry about. Extra ones or anything, or shorty tell. I have 8, 10, 12, 14, 16, 18, 20. Uh-oh. That's 4 too many. Back here, when we had 2 too many, we deleted 2 and moved 2. What are we going to do this time? We have 4 too many. I got lost. Okay, this time we're going to delete 2 pairs. And move 2 pairs. And I'm going to delete them off of the central atom. And let me go back to that other one and change this to, instead of delete 2, I'm going to go delete a pair and move a pair. Delete a pair and move a pair. Here I'm going to delete 2 pairs and move 2 pairs. And I want to delete these off the central atom. It's going to be easier. You can do other ones, but this is the easiest way. Delete that pair, and let's move this pair and move this pair. Could you move 2 pairs from one side? Yeah, actually you can, but let's keep it symmetrical here. When you're done doing that, you have this pair and this pair between sulfur and carbon, and this pair between sulfur and carbon, and this pair left, and this pair left, and this pair left, and this pair left. So when you're done, we go like this. And to get farther from each other, these would move over here and these would move down here. And that's what carbon disulfide would look like. Did I do that over here? Yeah, it would actually take this shape once valence shell electron pair repulsion theory kicks in. Basically, all that says is the electrons are trying to get away from each other. So instead of being bunched up on one side, they'll move out and fill up the space. Okay. We'll finish some more of them on another video.